Hi everybody. I think I'm going to record these questions because that way everybody can see the process. And if anything doesn't stick with these recordings, please let me know, and I'll go over those questions again. So today is our last lesson for this term, and I want to go over these questions for the ray model of light booklet. So I'm going to go over these two series of questions, and then you can go at your own pace and see how you go with those. So let's get into it. Okay. Yeah. So we'll go through our first set of questions. So questions 1, and the first one is about how much time it takes for light to get to Earth. Okay, so we've got a couple of values. We've got the speed of light. We use the variable c is equal to 3 times 10 to the power of 8 meters per second. We've got the distance. We usually use the symbol s, and it's the distance between the Earth and the Sun, and we say that is 1.50 times 10 to the power of 8 kilometers, but we've got kilometers, we want meters, so that's 1.50 times 10 to the power of 8, 9, 10, 11 meters. Okay, and we're nearly done. All right, so let's do that. So here you got Earth, here you got the Sun. We know that the light travels from here to there. We know that it's traveling at a speed of 3 times 10 to the power of 8. We can solve for the time. It's an expression that we've covered already briefly, which is the speed of an object is equal to its distance divided by time. Because we're after time, we just rearrange that expression. So time is equal to distance between the two objects, or the two places, divided by speed. Okay, that gives us 1.5 times 10 to the power of 11 meters divided by 3 times 10 to the power of 8. Gives us 500 seconds. If we divide that by 60, it's approximately 8.33 minutes. Okay, next question. Question 2. Okay, it says a ray of light hits a plane mirror at an angle of 20 degrees. Okay, theta incident. Guys, that says 200 in your book. Sorry, that was a mistake. That should say, it should have been a degree symbol, but for some reason the formatting converted it to another 0. So that's 20 degrees. They want to know, we know the angle that it reflects off has to be 20 degrees. So it's saying what is the angle between both of them? So if this one's 20 and that one's 20, then the total is going to be 40 degrees. All this will be 40 degrees. Okay? Okay. Question 3. Okay. And it says the intensity of light from a globe is intensity of light from a globe is 32 watts per meter squared. So intensity one, let's say, is 32 watts per meter squared, and that's at a distance of 4 meters. It says the intensity of the light at a distance of 16 meters. What the intensity of the light is, yeah, so what is the intensity? What's I2 when D2 is equal to 16 meters? Okay, we're using this relationship, V1 squared is equal to I2 D2 squared. So we'll plug in our values. So we've got 32 times 4 squared is equal to I2 and 16 squared. Okay. We can divide 16 squared on this side, divide 16 squared on that side, and then it looks like this. Calculator, that. Intensity 2 is 2 watts per meter squared, which is C. Answer is equal to C. Okay, moving on. Okay. It says the electromagnetic radiation that reaches the outer atmosphere of the Earth okay, this is the radiation on Earth's atmosphere is 1400 watts per meter squared. If the distance from the Sun to the Earth, okay, this is D1, is equal to 1.5 times 10 to the power of 11 meters. And the distance from the Sun to Uranus is D2 is equal to 2.8 times 10 to the power of 12 meters. Calculate the electromagnetic radiation at Uranus. So let's do that. So 1400 times 1.5 times 10 to the power of 11 squared is equal to I2. We got 2.8 times 10 to the power of 12 squared. I'll do each one separate. I2 is 3.15 times 10 to the power 25 divided by 7.84 times 10 to the power 24. We get I2 is equal to 4.2, 4.02 watts per meter squared. Okay, and number 5. Let's look at this. It says, remember that intensity is equal to this. That's fine. It says, what would be the intensity? What would be the intensity of the light shining on Earth with the power output of the sun? So we're saying power of the sun. E sun is equal to 385 iota. Iota watts, I'm pretty sure that is to the power of 24. Have a quick look. Okay, watts. Okay, the distance from the core of the sun to the surface, to its surface. So you got a couple of distances. So you got, let's call this D1, which is 695 times 10 to the power of 6 meters. And then the distance from the sun to the earth is this. D2 is equal to 1.5 times 10 to the power of 8 kilometers. We don't want 8, we want 9, 10, 11 meters. And the expression I want you to use is this. So we're saying the intensity on Earth is equal to the power released by the sun divided by the sphere that's created from the sun, from the sun's core, all the way to where we are, which is going to be D1 plus D2 squared. So it looks like this. You say this is the core of the sun. Say this is the distance to the layer, sorry, to the surface of the sun, which is D1. And then say you got Earth here, which is from here to there. It's D2. So the sun is effectively creating this big sphere of energy that it radiates to the Earth, and that's what we're trying to calculate here. So we could do that. Let's do that. Okay. So we got the intensity of light hitting Earth is equal to 385 times 10 to the power 24 divided by 4 pi. Okay, this is a big one. 695 times 10 to the power 6 plus 1.5 times 10 to the power 11 bracket squared. And that will give us a value of minus 10 24. Times okay, excellent. So that's 1, 3, 4, 9. Leave it at that. Watts per meter squared. That's the light that we experience, the intensity of the light that we experience on Earth, due to the, I guess, fusion power that's released by the sun. Okay, that's that question. We're going to move on to the second set of questions. All right, guys, let's go with these closed passage. Okay, so it reads, when a wave meets the boundary between one medium and another, any three things can occur. The wave energy can be absorbed, or the wave can be reflected or refracted. The law of reflection simply states that the angle of incidence equals the angle of reflection. The angle must be measured from the wave ray to the normal. This is an imaginary line which is perpendicular to the boundary. Concave mirrors reflect light into a focal point, can produce enlarged images such as a reflecting telescope. Okay. A convex mirror reflects light outwards. This produces images which are smaller, but have a wider field of view. A practical use for this mirror is driver side mirrors. So they're those mirrors that they give you that kind of fishbowl look. In communication, reflection is useful for long distance radio reception. Some radio wavelengths reflect from the ionosphere. We haven't actually spoken about the ionosphere, but it's just this region where the atmosphere gets really thin and it starts to get close to space. Okay, yep. Satellite dishes and microwave antennas, which are these kind of drum-looking things. These are the satellite dishes. So what happens is use reflection to focus wave signals into the receiver, right? So they're using this idea that kind of like a circular mirror, they're getting all the waves hitting on that circular mirror and reflecting it at a focal point. Okay, that one's that. Moving on to this, it says, refraction occurs when waves go from one medium to another. The waves may change in direction, wavelength, and velocity. Okay. For example, when light goes from air into glass, its speed slows down and and its wavelength gets shorter, although its frequency does not change. Okay. It also changes direction, going towards the normal. So remember, less dense to dense bends towards, more dense towards entering a less dense ones away from the normal. Snell's law describes the direct relationship between the sine ratios of the angles of the incidence and refraction, the angle of incidence and refraction. This ratio is called the refractive index. It is also equal to the ratio between velocities between the mediums, waves in two different mediums. So remember, it's always compared to the speed of light or between the different mediums. When a light ray is going from a slower medium into a faster one, the ray will refract away from the normal. As the angle of incidence increases, so will the angle of refraction until the refracted ray goes along the edge, this edge of the boundary. This angle of incidence at which this happens, angle of incidence which this happens is called the critical angle. And at angles of increase greater than this angle, total internal reflection occurs and the ray stays within the slower medium. This property is used in optic fiber technology to ensure that laser beams stay within the fibers. So I didn't include that, but it's like this. If you look at these beams, what happens is the refractive index of this optic fiber doesn't allow the ray of light to escape. So what happens is, as that light hits the different surface, it just continuously bounces back and forth until it makes it to the end. Right, that's optic fiber technology. Yeah. Okay. All right. Let's move on to the next question. Okay. Let's have a look at this question. It says that what is the refractive index of diamond if the speed of light inside diamond is that? So we know that the speed of light in a vacuum is that 3 times 10 to the power of 8 meters per second. The speed of light in a diamond is equal to 1.24 times 10 to the power of 8. So you can see it's decreased. So the expression for refractive index of a material X, the refractive index of diamond, is equal to the speed of light in a vacuum compared to the speed of light in a diamond. These are the same, cancel those out. We get okay, there's the calculator we're going to use. 3 divided by 1.24, 2.42. And it doesn't have a unit. Okay, moving on. Question 3. You got you got a whole heap of little calculations that you're doing for question 3. So it says just the fact that the refractive index of a material is the ratio, the speed of light in a vacuum to that of the dense medium. You will also have to consider that the speed of light in a vacuum is a constant, which is 3 times 10 to the power of 8. Use this information to solve for the unknown values. So the first one's done for us, which is in a vacuum it's equal to 1, whereas these ones we're missing something. So what we're doing is repetitive calculations, and we're using this expression. Nx is equal to C Bx. We know C is equal to 3 times 10 to the power of 8. It's a given forever, and everything is being compared to that. So you should be able to answer any value that you're missing, right? So you can see here we're only given Bx and we're only given Nx. We're going to have to use that. So let's do a couple of those. So let's do air, okay? So what do we know? We're told that Nx is equal to 1.00029, and they want us to solve for Bx, right? So let's do that. Rearranging that expression at the top, we get Bx is equal to C divided by Nx. So that is 3 times 10 to the power of 8 divided by 1.00029. That gives us something slightly smaller. Okay, 2.99 times 10 to the power of 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, meters per second. All right, let's do one more and then show you guys the answers. All right, so let's do water. Let's do something weird. Let's do silicon. Okay. I know we've never done something similar to silicon. We have. So we'll just do water. Okay, so what do we know about water? We know that it's, we don't know its refractive index, right? But we do know its speed, of the light of speed in water. So we know it's 2.25 times 10 to the power of 8, of course. So again, we're just using this equation, but we're solving for Nx again. So rearrange that back to how we had it before. Nx is equal to C divided by Vx, which is equal to 3 times 10 to the power of 8 divided by 2.25 times 10 to the power of 8. That gives us, cancel the because they're the same, 3 divided by, 3 divided by 2.25, yeah, 1.33 refractive units. So, yep, that's what we got there. Okay, let me show you guys the rest of those. Okay, guys, see how you went. Okay, let's have a look at number 4. So what is it that we know? It says, use the following diagram to find the incident angle. So we want to find theta I, theta 1 in this instance. No. What do we know? We know theta refraction, theta 2 is equal to 36 degrees. We know that medium 1 and 1 is equal to 1. And we know that medium 2 is equal to 1.5, right? So this is a Snell's law problem where the refractive index of medium 1 multiplied by the sine of of the incident angle is equal to the refractive index of medium 2 multiplied by the sine of the angle refracted. Okay, so let's put in our values. We've got 1 times sine theta 1. We've got 1.5 times sine theta 36. We find that sine theta 1 is equal to 1.5 sine 36. That's 0.88. Yeah. And how do we get rid of that? We take the inverse of the sine, inverse 1, sine, inverse 1. And then that's how we get our angle by itself there. So we find this looks like this now. 0.88. And that gives us an angle. Shift. Oops. Shift sine 0.88 gives us an angle of 62 degrees. 62 degrees. So this angle here, theta 1, is 62 degrees. Okay, let's move on. Okay, all right, so here we go to another situation where we do rapid fire calculations, and it's always the same thing. So we're using Snell's law, right? So remember, it's N1 sine theta 1 is equal to N2 sine theta 2. You're just using that constantly and you're figuring out what you're missing. And you're always comparing it to air. And we're saying air is equal to 1. So you could almost just say N1 is always going to be equal to 1, right? But theta 1 is going to vary. It's going to vary in value. They're going to give you different ones, which is going to be this one, right? So 60. So we'll do these three, and then you can do the rest. So let's do diamond. Okay, diamond. And what we have is the refractive index of N. Okay, so we know N1, that's going to be 1. Sine, what angle is it hitting? It's hitting 60 degrees, awesome. We've got the refractive index, which is 2.42, and we don't know the angle of refraction, which is sine theta 2. So we can solve for that. Okay. Number 1 is like it's nothing, so you just do sine 60 is the same as 1 sine 60, the same. 0.86 looks all right to me. 87. Divide this over 2.42. 0.87 divided by 2.42 is equal to sine theta 2. It's kind of the same thing that we did before. So we take the inverse, we get that's equal to sine 5, 6. It's 21 degrees. Okay. So let's do ice. Okay. Ice 1 sine. We've got the incident angle. No, we don't have the incident angle. So 1. But we have everything else. We've got the refractive index of ice being 1.67. We got its angle of refraction, sine is 33. Okay. So after that, so we get theta is equal to sine to the power of 1.67 sine 33 divided by 1. Same thing that I've done here, I've just done it more consolidated. Divided by 1 is like not including anything. 1.67 sine 33. Okay, that's an angle incidence of 65 degrees. Okay, all I've done there was I just skipped a couple of steps rather than simplifying, and 1 is, yep, it's almost like nothing. That's all right, so 65 degrees. And we'll do the last one, which is acetic acid vinegar. Okay. So what are we missing here? We're missing the refractive index of vinegar. So 1 sine, what's the angle of incidence of the light in air? It's 53 degrees. Right? We don't know its refractive index, which is N2, but we do have its angle, which is 35.36. And what we're solving for this, aren't we? Okay, so let's do that. We can just divide this side by that, so we get 1 sine 53 divided by sine 35.36, and that's N2. Find out that N2 is equal to, remember, you don't have to include that step 1 because it's like doing the same, 1 times whatever is equal to the same value. So sine 53 sine 35.36. Okay, 1.38 is the refractive index of acetic acid. Okay. I see how you went. Okay, I've simplified this one to 65, but it says 65.24. 21, we got that one fine. And this one was 1.37. Okay, maybe that's 1.37, 137. But yeah, that might have been, I rounded it up differently. But let's see how you go, guys. Make sure you do these questions because this is good practice. You're not going to get any more practice other than this. And come the exam, you should be good with doing these rapid fire calculations. Okay. Okay, guys, look at question number 6. In this instant, we have, it looks confusing because you're saying that medium 1 is this one, and we're normally treating medium 1 as the one where the arrow is coming through, or the source is coming through. And there's this obscure angle here. So disregard this angle 1 here. It's really angle 2. So I mean, think of it like this: as long as the medium, the refractive index pairs with the angle that it is experienced in that medium, then that's fine. So as you can see here, I've paired the refractive index with the angle there, which is sine 30. And I've done medium here, medium 1 with the correct angle. So I've got 1.5 and sine 60. And I find that it's got a refractive index of 2.59, medium 2. Okay, let's move on. Okay, question 7, guys. This is a good question because it's asking you to do a fair bit of things. And I guess this gives me an opportunity to kind of go over how graphs can be used in physics to calculate things and why they're important. So yeah, this is a really good question. So let's have a look at this. It says a student wants to experimentally determine the refractive index of an unknown transparent substance. They know that the refractive index of air is approximately equal to 1. Okay, we've got 1 known. They attempt to obtain the most appropriate angle of incident and refraction, but it is impossible. But it is impossible, to tell with absolute certainty. They derive an experiment where they approximate several incident angles to that of the corresponding fraction angles. So what they're doing is you've got this mystery material. It's in a semicircle, and the reason why it's in a semicircle because as that light coming from air hits it, okay, it bends towards it. Obviously, it's denser, but what happens is because it doesn't have any like edges or any like jagged edges or anything, it just goes straight at that angle, so it makes measurement easy. So that's why it's circular. It's almost like at any point where the light hits at these at this circular boundary, the light's just going to go straight. So that's why they got that set up. So what they're doing is they're shining this light at different angles, 90 all the way to some kind of zero, not zero, maybe 10 all the way up to 90. Not even 90, maybe 80 or whatever. And they're seeing how that angle behaves. Okay. Okay. So yes. Okay. And these okay. The students recorded the sine of the incident angle, which is this value. So that's this sine of the incident angle, and the sine of the refraction angle, which is this one here. Okay. Calculate the corresponding angles of the table. Okay, so that's quite easy, guys. All we have to do is just use our calculators to calculate these unknowns. So we'll do that. We'll do an example. Okay. So what they got here, sine incident, it's like what's written up there, and the sine of refraction is like what's written up here. So it's like this. So it's like they haven't given you the angle. They've got the sine of some mysterious angle that you're trying to solve gives you that value here, 0.174. And the sine of some mysterious angle is going to give you this value here, 0.043. So if we do those for every single one of those calculations, that's what we're after. So it looks like this. We know how we do this. We have to, in order to get the angle, we have to take the inverse. Right? 0.179. That's going to be the inverse of that, 0.043. Sine 0.179. That gives us 10.3 degrees. And the other one, the angle of refraction was 2.46 degrees. So you have to repeat those calculations over and over for these. So let me show you how you do that. Make sure you do these, guys. You need practice, get that practice down packed. All right, so, okay, so you can see what the guy's doing, well, whatever the student's doing. They've started off at 10 degrees. They've changed it to 20 degrees. They've increased, they've gone up by 10 and they've stopped at 60 degrees. And what they've done is, that is the incident angle. That's this angle here, theta 1. They've increased it, they've gone by 10 degrees to the normal. So 10, 20, 30, and at some point over here, they'll be at 60. And what they've done is, they've noticed this angle is increasing as well, but you can see it's being refracted a whole heaps as well. So it's almost twice the value. So you see if they're going to hit 10, they've doubled the value, it's about the same. Tripled, yeah, it's almost going up by a predictable increment, and we're gonna figure out that increment in a second. Okay, now it's asking you to graph this. They want you to do a graph that's going to look like this. You're going to have the sine of the incident, theta I, and you're going to have sine refraction. And you're going to have some weird graph that's going to form. Hopefully, we should get a nice straight graph. It should be, as something increases, the other thing increases by some kind of rate as well, or decreases by some kind of rate. It should be increasing as well. But that's what you're plotting. So you have to set up your graph. How are you going to do it? So let's have a look at your sine. Remember, you're not doing the angle, you're doing just the sine. I mean, you could do the angle, but here they want you to do this. And I mean, the numbers are going to be a bit easier if you do it this way. So the incident, what's the highest number that you're going to have to get up to? So the highest number you got is 0.864 sine theta incident. So, okay, 0.86. I mean, you can round that up to about 0.9. 0.9 is going to be your largest number. What about sine of the refraction? Your highest one there is 0.216, so about 0.22. 0.216. 0.22. And I mean, here we're going to have to round anyways. We're going to have to round higher to make our life easier. So maybe 2 figures. So here 0.174, we'll get rid of the 4. This one's all right to 0.34, that's fine. 0.5 is great. 0.6 is good. 0.76, just increase that to 0.77. That one's going to be 0.9, and you're going to do the same on this side. Okay, now the next thing that we need to do is decide how we're going to set up our, I guess, our scales. So here we got the paper that you're going to be using, and I recommend you use a pencil for this. because it just makes life a lot easier if you make a mistake and you plug it out. So, okay, here we got, that's going to be 0 at this point. That's fine. We sine theta reflection. I don't have space there, so I'm just going to write here sine theta incident. Okay. And I know that with my incident one, I'm going to go up to 0.9. I just got to figure out how I'm going to fit it in here. I can't go up by squares of 10. I'll probably go up by squares of 5 intervals. So that'll be 0.1. I'll go all the way up to 0.9. Okay, and then, okay, we'll do that. Okay, so I got that set up. Now I've got to fix my x-axis. Now, I found out that my highest number in my x-axis is, on my horizontal axis, is going to be 0.22. So I just can't go up to 0.2. I'm going to have to go either 2.5 or 3. In this instance, I might go 3. Now, if I go up in blocks of 5, that's going to be my graph. So I'm going to take advantage of all the space that I go, and I'm going to have 20 spaces between each one of those. So that's going to be 0.1, it's going to be 0.2, it's going to be 0.3. Okay? Okay, the next things that we have to figure out is how much is each one of these squares worth. So in the vertical axis, we have each 5 squares is worth 0.1 divided by 5 squares. That's going to give me 0.02. And on the horizontal, we have 20, so 0.1 divided by 20. Each one of those squares is going to be equal to 0.005. So here we can get like a whole heap of accuracy in terms of these values at the top here, whereas in the vertical axis, we're kind of limited. But remember, we're rounding up, so to 2 figures, and hopefully that's going to simplify things a fair bit. Okay, let's start plotting. Okay. So our first one, we have 0.043. Okay, so we know that's 0.1, half of that's going to be 0.05. Okay, so right next to that will be 0.045. And we're rounding to 0, so that's going to be 0.04 is going to be there. And our top one here is 0.17. So we know that's 0.1. Each one of these increments is 0.02. So 0.12, 1.4, 1.6, 1.8. So in between 1.6 and 8 is 0.17. So our first plot is here. Okay. Okay. Let's have a look at our next one, 0.085. So if that's 0.05, a quarter of the way up, or 3/4 will be 0.075. That's going to be 0.08859. So we're rounding up to that, 0.09. Remember, see whichever ones you have to round up. That one's going to be 0.13. That's going to be all right like that. You can probably do that one at 2. That can be 2.2. And These ones, that can be a 9, that can be an 8, that one stays like that, or 0.6, 0.5, okay? But anyways, we're doing this one here, 0.3, which is going to leave that, so that's this one here. So those intersect at this point here. And that's where we're going to put our plot. And make sure we're using X. So I'll do the rest of these. Okay, so I've just realized I've put that as 0.3. Now here we got, remember we're rounding up to 2 figures, right? So 3, 4 is fine, 5 is okay, 6, 4 is good, 7, 7, and that's probably going to be 8, 8, 7, okay? So 0.34, that's okay to do. So 3, 2, 3, 4, so that has to come up a bit. So that comes up here. Okay. I'll do the rest of those. Okay. So knowing this one here, that's kind of like the dot points of the crosses that you should get with all those values intersecting. Just remember, if you want to know what each value is, just multiply the quantity of squares up to that particular point by that factor, or whatever factor the x-axis had, and that should give you that value at that point. So at this point here, I was supposed to plot 0.22, which is what I've got. So if you do 0.005 times, you got 10, 20, 30, 40, 4. I got 0.22. And you can do that the same. And then in my y-axis, I rounded that up to a 9, 0.866. So just 0.9. Now what you do, you need to do your line of best fit. So this is kind of averaging out all the errors. You can see that's about half. You try and balance all the things between them. This is a pretty good data set because you can see it just goes straight to the origin. You can see there's a lot of accuracy in this data. That's very good. And what happens is, if that one was going more towards the y-axis, or more towards, or intersect with the x-axis, or it intersects the y-axis earlier, that's suggesting that these two variables are not easily or directly related. There's got to be something in between. There might be an error, there might be some kind of scratch, there might be some kind of angle in the lens. But here we got a nice setup, and that's perfectly good. Okay, so we've got our line of best fit. And now we're expected to do some other stuff, so let's do that. Okay, for C, it's asking us to take the slope. I'm going to move over here. This is question 7C. Slope. Now all we have to do is find 2 points that make our life easy. This point here doesn't intersect perfectly there, but it does here, so that's perfect. So we're going to use those 2 points to calculate our slope. Okay, and the distance here and the distance there, those 2 variables, we're going to, so those 2 grid points, we're going to use to calculate our slope. So in order to calculate the slope, there's a general expression, which is the slope is equal to rise over run, or you can use the difference between two y values, there's two dot points, over the two x values in those dot points. Okay, and this is just an exercise. If you don't get it, that's fine. We've still got time to practice these more. So let's look at these two points. All right? So this point here is governed by a coordinate. So it's the x coordinate first, comma, the y coordinate. Okay. So our x coordinate here is 0.1, and comma, our y coordinate is 0.4. Okay, now let's have a look at this coordinate here. So that's 0.5, comma, and it's 0.2. Okay, so we can use that now. So we can say our y value, y2 value was 0.4 minus our y value O1 was 0.2. X value in the higher one was 0.1. And our x value in the lower one is 0.5. Okay, so let's have a look at that slope. Okay. Now that's not 0.5, sorry. 0.5 would be all the way somewhere up there. That's 0.05. So that point there is 0.05, and the y value was 0.2. Okay, so that makes a bit more sense. So yeah, 0.1 minus 0.05. It gives us a value of 4. So our slope is 4. Now, that's interesting because if we move on to the next question, D, okay, demonstrate how the slope equals the refractive index of an unknown material. It asks you to do some kind of critical thinking over there, right? So what this graph is saying, this is the equivalent of writing this. Sine theta 1 divided by sine theta 2. Refraction, incident. That's what this graph is. You're plotting each one of these data points. You're dividing each one of these data points in essence when you plot them. That's what you're doing. And what happens is, as you do that, it consistently does. Each one of those value consistently increases by this slope, and that's what's happening here. But we've done something similar like that. We've done something similar like that. This looks like Snell's law, right? Looks like Snell's law. This looks like Snell's law, right? So we'll come back to this. So we know Snell's law is N1 sine theta incident, right? So you got situation was this: you had that, you had this, you had your normal, you had incident, and you had refraction, right? So this looks like Snell's law because N2 is what we're trying to solve, sine theta refraction, it's incident. This value is equal to 1 sine theta incident, and N2 is what we're trying to figure out. Right? Because that's equal to 1, it's nonsensical. We don't even have to consider it. So this is just written like this: sine theta 1 incident is equal to N2 sine theta refraction. Right? But if we move this to that side, we divide this side by sine theta refraction, this side by sine theta refraction, we get sine theta incident is equal to sine theta refraction is equal to N2, right? That's what we got up here, N2, right? So if we assume that air has a refractive index of 1, we can say that we can calculate that refractive index of this unknown material, which happens to be 4, okay? The slope gives us that. So that's quite interesting, right? So not only is the slope equal to that, the slope is also equal to sine theta incident angle, sine theta the refractive, refractive angle. Only for this incident situation. Okay, and then you scroll down and it says, looking at the chart, question 3, which material you reckon this is? This is it. If you scroll up, you have these materials, and if you look at silicon had the higher refractive index of number 4, and because this is a number 4, we can assume that this material, E, question E, the refractive index, the material must be, must be silicon, because Nx is equal to 4. All right, done. Let's move on. Okay, nearly done, guys. Question 8. You got, for the following problem, break it down as if it were 2 problems. Find the refractive index of medium 2, and use that information to solve the angle of the exiting beam, which happens to be medium 1. It could be, it could be light entering water, or light part. Sorry. Yeah. Okay. It could be, yeah, light passing through air into some, like a glass window. It gets refracted and then ends up in air again, and then gets refracted again. All right. So we've got to figure out what that final angle is and what the refractive index of this material is. So all you have to do is just treat it as 2 problems, and we shouldn't have a problem. So let's have a look at that. So what are our unknowns? So we have N1 is equal to 1.3, N2 we don't know. We know theta 1 is equal to 6 degrees. We know theta 2 is equal to 29 degrees. We don't know theta 3. And we do know N3. N3 is also equal to 1.3. That's all. So we've got a whole heap of stuff. And the reason why we have a whole heap of stuff is because, well, we have multiple steps. It's almost like we've got 2 problems in one. And I think that's the difficulty about this problem, is considering it, breaking it down into 2 problems. That's the difficulty of that. So let's do the first part. All right? So this is the first part. You got it coming in at 60. You got it refracting at 29. You know, N1 here is equal to 1.3. N2, we don't know. So let's solve for N2. 1.3 sine 60 is equal to N2 sine 29. find out that N2 is equal to 1.3 sine 60 divided by sine 29. We find out that it's got a refractive index of 2.32. So that's the first part of the problem done. Move on to the second part. So what happens is, yes, we got that happening, and what's occurring is light is hit here. It had some angle here, and it's got some other weird angle there, and it's refracted away. Right? And we don't know that angle 3. So we know this angle in this corner is going to be 29 because that angle is, sorry, that line intersects parallel lines. Just rid of this. That angle here, 29 degrees, is the same angle here. So it's a bit of a trick here. So it's 29 degrees. And we know this medium here is 2.32. Right, this is N2. And N3, we know that's equal to 1.3. We want to solve for that angle. Let's do that. So 2.32 sine 29 is equal to 1.3 sine theta. Right? We want to solve for the angle this time. So 2.32 sine 29, 2.32 sine 29 divided by 1.3 is equal to sine theta. Theta is equal to the inverse of this. Two point 32 sine 29 1.3 so that's 60 degrees. Right. Now, guys, don't get startled about this. You're doing the same thing. Just rather than breaking it down each step, you're just kind of moving everything to one side and rearranging it. I swear, if you just do everything by steps and do the same procedures, then you're going to get to the final answer as well. Now, back to this. Conceptually, this makes sense because it's in the same medium, the same angle that it comes in. It's almost like this medium shouldn't exist, the medium in between, and it's almost like it just continued in a straight line. Because there was this medium in between, that separated this one that had a refractive index of 1.3, it changed a little bit in direction, but it refracts at the same angle that it incidents because it's the same medium. That's why if you see a problem like that, they got the same refractive index, don't even bother with the well, if it's asking you to do the calculations, do the calculations, but you would expect it to refract at that same angle that it incident to, which was 60 degrees. Okay, let's move on. Question 9. Here we go. Question 9. It says, calculate the critical angle of silicon exiting into air, where silicon has a refractive index of 4.01 and air has a refractive index of 1. Okay, remember that the critical angle had to do when the light refracted at 90 degrees and that meant it just followed that boundary line. We just have to use the expression for it. Okay, which was this. So N2 is the refractive index of medium. Sorry, that's N2, medium 2. So that's where it's trying to exit to, which is 1, which is air, and N1 is the refractive index of the denser material. Okay, so let's have a look at that. Okay, so it looks like that. Less dense medium is N2, more dense medium is N1. So this is kind of the situation. It could be either way, but in this instant, this side's supposed to be the denser medium. So we got N1 is equal to 1, which is air, and 2, the refractive index of silicon, is equal to 4.01. And they expect us to calculate this critical angle, where it ends up being at 90 degrees. So we're using that. So the setup is this: sine of the critical angle is equal to medium 2 and medium 1. So sine of the critical angle is equal to, sorry, less dense medium. So guys, swap these around. Okay, denser, less dense. So that becomes this. We get N2 is equal to 1, and 1 is equal to 4.01. So again, we take the inverse, is equal to sine. Guys, if this is not making sense about the inverse, let me know. Shoot me an email, and I can send some notes to you about that. Or I can send some emails back to you about it. Because it is a popular thing that we do. It does come up a fair bit. So it'd be good for you to be okay with that. Let's do that. Shift sine 1 divided by 4.01, 14.4, 14.4 degrees. So that's saying that this angle here is 14.4. So if you go any further this way with that light, it's all going to bounce inwards. Right? So it's all going to bounce inwards. So that's as much as you can expand from the normal. Right? So, 13, 10 degrees, you're going to refract it out. You're going to actually get it out. You're going to refract it out, and that's going to go somewhere like that way or something. But yeah, once you get to 14.4 degrees, it doesn't come out. And if you increase it by increase 14.4, it's going to start reflecting inwards. Okay, let's move on. 10. Okay, it says here. Okay, all right. It says diamond. Okay, so what do we know? The diamond has a refractive index of 2.4, which is the variable n. Find the critical angle. Nice. So we know this sine of the critical angle of diamond, assuming that that diamond is the denser one, and it's trying to exit into air, which is what's happening here. You've got some light inside the diamond. It hits that critical angle. It internally reflects. So it's greater than the critical angle. It internally reflects, and then it hits another surface at the right angle, and it can actually exit the diamond. So let's have a look at that. So that's 1, 2.4. Diamond is equal to 1 divided by 2.4. So the critical angle of diamond is 24.6 degrees. So what that's saying is, you got this setup here. So you got diamond, you got your normal, you got this angle here. That is 24.6 degrees. At this point, it's going at 90 degrees. Right? And that's air. If you start increase it that way, and it's going to go internally reflect. If you go more towards this side, then you should start seeing that light refract out into the air. And that's kind of what the situation's happening here. So it's asking, so that's for A. B, it's asking what would happen if light inside a diamond hit the boundary at an angle of incident of 20 degrees. So if we hit it at 20 degrees, it will refract out, right? That's kind of what we were talking about here. It'll refract out of the diamond. Out of diamond. And for C, at 30 degrees, well, at 30 degrees, it will internal reflection of light. It will internally reflect. So that's kind of the cool thing about diamonds. So when you have them in your ring, they tend to keep a lot of light in it. And that's why they look very bright, because they cut them in a way where the light, I wouldn't say it gets trapped in there, but it tends to bounce around more in diamond. So